Hello friends, so here is another question on projectile motion with horizontal projection. It is given that a particle is projected horizontally with a speed u from the top of an inclined plane at an angle theta with the horizontal. How far away from the point of projection will the particle strike the plane? Okay, so here if you see, this is an inclined plane. Okay, this let's call this point A and this point B. Okay, this AB is an inclined plane. It is at an angle theta with the horizontal. So what the question is saying is that a particle that is projected horizontally with a horizontal velocity u from point A. So obviously it will undergo projectile motion, and let's say the particle it hits point B. Okay, so the inclined plane it goes on and on and on, but here I have limited to this point. Let's say the particle it hits at point B. We want to find this distance AB. Okay, this distance AB, and we want to find it in terms of the constant values, that is this angle theta, inclination angle, the horizontal velocity u, and the acceleration due to gravity, which will come into play. So we want to find an expression because there are no values given, numerical values, so the result will be in the form of an expression. Okay, so here first we have to determine the parameters that are involved. So as you can see, when the projectile it hits point B, this is the distance on the inclined plane AB which it covers, but the net vertical and horizontal displacements are, let's say this point is O. Okay, so the net vertical displacement SY is equal to OA, and the net horizontal displacement SX is equal to OB. Okay, so this distance D, we can determine it as Sx square plus Sy square root over, because AB is equal to root over of OB square plus OA square. This is the expression, this is the result that we are going to get. Now we have to find expressions for Sx and Sy. Now here this u is nothing but the horizontal component of the initial velocity ux. Okay, this is clear, we have discussed it in so many questions. Then there is no component of initial velocity in the vertical direction, either upward or downward. So uy is equal to 0 meter per second. Okay, next, acceleration due to gravity is acting downwards, it is supporting the downward motion. So ay is equal to plus g, which is equal to 9.8 meter per second square, but here numerical value is not required, so this is not required, so we'll simply keep it as plus g. Okay, we'll keep it as plus g. Okay, next is the acceleration or deceleration along the horizontal axis, the horizontal side. There is no acceleration or deceleration, so ax is 0 meter per second square. Okay, this much is clear. Now we have to do the analysis as per principle of independence of motion. X component analysis different, y component analysis different. Now Sx is equal to uxt plus 1 half ax t square. Okay, this. Now ux is 0, ax is 0, okay, ax is 0, so this whole term, it will become 0. Ux is equal to u, and here for the entire projectile motion, when the particle, it covers the net horizontal displacement of Sx, the total time which passed, that is called as time of flight. So we'll substitute t with time of flight Tf. So Sx is equal to u into Tf. That implies Tf is equal to Sx by u. So we will keep it in a box because we'll use this equation in the next series of analysis. Now Sy is equal to uyt plus 1 half ay t square. Now I'll make the substitutions. Here ui is 0, there is no vertical component of initial velocity, this whole term becomes 0. Ay is equal to g, and again for the entire vertical displacement, the time will substitute with time of flight Tf square. That implies Sy is equal to 1 half g Tf square. Okay, 1 half g Tf square. Here we'll substitute this value of Tf. Okay, so what we are trying to do is we are trying to express Sy in terms of Sx. Okay, so we'll make the substitution. So Sy is equal to 1 half g Sx by u whole square, which is equal to g Sx square by 2u square. This is equal to Sy. Okay, this is the expression of Sy. Let's keep it in another box and give it a name, equation number 2. Now if you see here in this diagram, here tan theta is equal to OA by OB, that is Sy by Sx. So tan theta is equal to Sy by Sx. That implies Sy is equal to Sx tan theta. Okay, so this is another equation that we have got, another relationship, equation number 3, let's say relationship number 3. Now pay attention to equation number 2 and equation number 3. Here Sy is equal to gsx square by 2u square, and here Sy is equal to Sx tan theta. So both represent Sy, so we can equate them. That implies Sx tan theta is equal to g Sx square by 2u square. That implies g Sx square by 2u square minus Sx tan theta is equal to 0. That implies if we take Sx common, we will have g Sx by 2u square minus tan theta equals to 0. Now here Sx cannot be 0 because we see here in the diagram Sx has a finite value. It cannot be equal to 0 because there is some net horizontal displacement of the projectile. So Sx cannot be 0 in this relationship. So the only way this thing will become 0 is when gsx by 2u square minus tan theta, that becomes 0. So that will be the case here. So that implies Sx cannot be 0. Let me write it here. From the diagram, it is clear that Sx is not equal to 0. So gsx by 2u square minus tan theta, that is equal to 0. That implies gsx by 2u square is equal to tan theta, or we can write Sx as Sx is equal to 2u square tan theta by g. Okay, this we have represented Sx in terms of u, tan theta and g. Now going back to the expression of d, which we calculated at first, d is equal to Sx square plus Sy square root over using Pythagoras theorem. So here we'll make that substitution. So that implies d here is Sx square plus Sy square. Okay, that implies that equals to Sx square plus Sy is what? Sx tan theta. Sx tan theta whole square. We have just substituted Sy with Sx tan theta because we want to bring it in Sx form, because we have got this relationship Sx. So this is equal to, taking Sx square common, Sx square into 1 plus tan square theta. Now 1 plus tan square theta is equal to sec square theta. So this is equal to Sx square sec square theta. So this becomes Sx sec theta. So here we'll replace Sx with this. So this becomes 2u square tan theta by g into sec theta. This is the expression of this horizontal distance, the net distance in the plane. Okay, how far away from the point of projection in the plane the packet or the object it falls. This d, AB, this AB distance, that is equal to this expression, 2u square tan theta sec theta by g. Okay, so it is a bit complicated, so there are a lot of steps, lot of terms that we have equated. So you can pause the video whenever you are confused and you can watch it.